So you should have just done a little activity where you folded some paper and you got a parabola looking thing after you did all your folds. So the point of that was for you to realize that you can define a parabola as all of the points equidistant from a point, which we're going to call the focus, and a line, which we're going to call a directrix. So you should see that parabola that just popped up there. My focus is going to be interior. The parabola is always going to wrap around the focus. So I'm going to label that as F. And then my directrix is going to be a line down here that's parallel to the x-axis, like this. And that's my directrix. Maybe I'll just make it solid. So the idea is that, and this is not to scale, but the length from here to here should be the length is the same as the length from there to there. So if this was to scale, this parabola would be way more wide, you know, because maybe this point out here, if it was that wide, would be the same as this distance and that distance. But the point is that we have a focus and a directrix. So whenever we have a parabola, I can write the equation in a form that, you know, normally we think of a parabola as a y equals x squared something, but I can change the way that the equation looks and have x squared equals 4 times p times y. And what that does is it helps me figure out the distance from the focus and the directrix and all that stuff. So this p value right here is going to be this length right here. That's p. So from focus down to the vertex, the low point of the parabola, and then also this right here, that's also p. And the reason why they're both p, why this length and this length are the same, is because they're equidistant. So the distance from here to here has to be the same as the distance from here to here. So we'll write out p equals distance from vertex to focus, or vertex to directrix, and I'll abbreviate that. So all I'm saying there is that this length is my p and that length is my p. So let me do two little examples. I'll do, say p was equal to 3, and we'll talk in a moment about changing x squared versus y squared, but we're just using x squared for now. So say I had p equal to 3, a positive 3, so that would give me x squared equals 12y, because when I multiply that 4 by the p-value of 3, it would give me 12. What that's going to do is give a parabola that goes like this, and then this distance up here from here to here is 3, and then my directrix is down here, and that distance is also 3. If I make the p negative, so for example, say I had x squared equals minus 12y, well, that would be p equal to negative 3. All that does is flip the orientation of the graph. So here I've got parabola that opens up and has this length is 3 and that length is 3. So by putting a p-value that's negative, it's going to be the same thing except for it's going to be upside down. So I'm going to go ahead and draw it in like this. I'm going to go and sketch my parabola in like that. And I'm going to label my focus. And this length is 3. And then I'll go and put a directrix up here. And this length is also 3. So I'm going to get rid of this slide in a moment. We're going to do two quick examples. So make sure you've got written down what you want to write down. Real quickly before I move on, I did say a moment ago that this is an x squared equation, so it opens either up or down. If I have an equation like y squared equals 20x, then I want to figure out what my p-value is. So this is 4p, so I get 4p equals 20, which means that p is equal to 5. Now, since I have a y squared equation, that means that it's going to either open left or it's going to open right, as opposed to up or down with an x squared equation. So, since my p-value is 5, it's going to open towards that positive direction. So if I wanted to graph this thing, I would go ahead and sketch my axes in. I would sketch the parabola in like this. I know it's going to open out to the right like that. I'm going to take 1, 2, 3, 4, 5, put a dot, label that as the focus. It is at 5, 0. And then I'm going to go 1, 2, 3, 4, 5. And then I'm going to put a dotted line for my directrix. I'm going to label D, colon, oops, it's not a y equals. Since it's a vertical line, this is all the points x equal to -5. So I'm going to explain real quickly, hopefully, how we go and we find these two spots right here. I'll put a disclaimer out there that my drawing is not to scale. My x scale and my y scale are not the same, and you'll see that in a moment. So, if you remember that, well, this length is 5 and that length is 5, and that's because this parabola is all the points that are equidistant from this point and this line. So that means that this length right here has to be the same as this length right here, and this length right here has to be the same as this length right here. So you can see already that, well, if those guys are the same, then the scale is not the same. So this y scale and the x scale are not the same. So I want this length and this length to be the same. So I can actually figure out what those lengths are really easily. If you look, you'll see, oh, this guy, well, that's 5, and that's my p-value, you know, because this length is 5, so that makes this length straight down to here 5. And then this length is also 5, so that makes the whole length from here to here 10. And since this length and this length are the same, they're equidistant, this point is supposed to have the same length from here to here as it has from here to here. This point, same length here to here, here to here. So this point, same length here to here and here to here. So, since that's 10 and I know what it is, then I can label, I know that this guy is 10 as well. So, if I wanted to put the coordinates of that point right there, I know it has the same x coordinates as that, so it's 5, comma, it's 10 up from the axis, so it's 5, 10. I could do the same thing down here with this other one. I know that this length from here to here is 5 plus 5, which makes it 10, which means that this length is 10, but it's going down 10, so it gets coordinates 5, 5, comma, -10. This thing right here, this bar from green dot to green dot, is actually called a lattice rectum, and sometimes you see that term on standardized tests and stuff like that. So I'd like you to go ahead and try to graph this one right here, using the same ideas that we used for this one right here. Notice I'll give you a couple of little hints to start. I do have a y-squared parabola, so that means I'm going to be one of these two. You should be able to find out your p-value. And notice that the p-value is actually negative, so that's going to change something with the way that the parabola looks. I'll leave it at that. You should pause the video and go ahead and try that yourself real quick. So the first thing I would do is say, all right, well, I know that this is my 4p value, so 4p is -16. If I divide by 4, I get p equals -4. So now I can use that. I'm going to sketch my grid out. Since it's -4, that's going to flip the parabola around the other way. So I'm going to draw a parabola that opens to the left, like that. And then I'm going to tick out 1, 2, 3, 4. I'm going to put a dot. That's where my focus is. I'll say its coordinates are -4, 0. And then I go 1, 2, 3, 4. Put a dotted line for the directrix. Put some arrows on it. Label D. Oops. And that is x equals +4. And now, if I want to label the those two like corresponding green points, I can count that this length is 4, this length is 4. So that means that if I draw a dot here that corresponds with that piece, that is 4 plus 4. I'll just go 4 plus 4, which is 8. Which means that this length is also going to be 8, because of that equidistant property of a parabola. So that green dot, it has coordinates -4, comma, +8, and then I get a flipped version of it down here, which is -4, comma, -8. And that's totally 100% complete. Hopefully you got that too.